Hi everybody, this is Cal with section 6.1, the derivative, and section 6.2, the mean value theorem. There's a lot to cover in these sections, and we're not really going to do the entire sections. We're going to kind of pick and choose things. 6.1.1, your book gives the definition of the derivative, and this is more or less a definition that you're familiar with. You should kind of compare how the given definition here compares with what you know from Calc 1, which is sort of restated down here. I would read this note in the bottom middle of the page, and I would read the following bits reasonably closely. Going on, 6.1.2 is pretty important. This is a theorem that is pretty central. And the remark in the middle of the page is pretty cool. You could read that. It's a really great pathological example. Okay, 6.1.3 is pretty meaty. I would read that pretty carefully. I would try to prove parts A and B by yourself, and I would read through the proofs of C and D. These are fun things. You've probably always kind of wondered how proofs of the product and quotient rule go, and you get to see them here. Product rule isn't so terribly hard, actually. Quotient rule is a little bit wonky, but it's not too bad. And the corollary, which extends the product and quotient and so on rules to finitely many functions, is also pretty cool. Do read the notational note in the middle of the page. Now we get into the fun stuff. We're going to prove the chain rule, and in order to prove the chain rule, we're going to establish something called Carat-Theodory's theorem, which I'm going to leave you to try the interpretation. We're going to talk about it in class, and I'm also going to ask you to try to draw out what this means on your reading quiz. This is a theorem that's a little hard to understand just from the statement, but if you try to draw it out, then you learn pretty quickly what's going on here. So I'm going to leave that to you. And the proof isn't so terribly hard. And to get the picture, you could try reading this blurb, although I will say the book doesn't do the world's best job right here. The important thing for us is how Carat-Theodory's theorem is going to help us prove the chain rule. You can kind of read here how we would like to prove the chain rule. The issue with this approach is that if f of x minus f of c is equal to 0, which it very well may be for x near c, then we have a really big problem here. We have a dividing by 0 kind of problem. And what Carat-Theodory's theorem lets us do is approach this without ever having division in our problem, which is really useful. So the proof of the chain rule is going to use Carat-Theodory's theorem. We're going to go over this in class. It's pretty cool. It's not as bad as it looks. Do try to read through it. Moving forward from there, we have some examples in 6.1.7. That's fun stuff. You probably don't have to pay too much attention to example D with the sines and cosines, but I mean, this is stuff that you know. Certainly these are examples that you can handle. I am not going to delve too terribly deeply into the section on inverse functions, mostly because we didn't cover section 5.6. That being said, it's worth a read through the rest of the section to kind of get a sense of what's in here. This is stuff that you know from Calc 1, or could figure out without too much trouble. So I would give this a light read, but focus more on the results in this part of the chapter instead of the proofs. And again, these are familiar results from Calc 1. Moving on to 6.2, the mean value theorem. Again, we're going to pick and choose things here a little bit because it's a pretty big section. We start by developing the ideas of relative maxima, minima, extrema, You know these as local mins and maxes from Calc 1. And we have what's called the interior extremum theorem. In Calc 1, you might have known this as Fermat's little theorem, or yeah, just Fermat's little theorem. It says that the derivative at relative extremum has to be 0 if the derivative exists. This is the idea of critical points from Calc 1. The places to look for local extrema are places where the derivative is 0 or doesn't exist. Which is stated here in this corollary, 622. Now we get to Rolle's theorem, 623. This is old hat from Calc 1. It says that if f starts and ends at the same height, and if it's continuous and differentiable between, then there's a place in the middle where its derivative is 0. This should be pretty obvious if you draw a drawing, which your book was actually kind enough to do. And from Rolle's theorem, it's very easy to prove the mean value theorem, which is the same mean value theorem that you know and love from Calc 1. And the picture is the cool part. The remark over here talks about the geometric view of the mean value theorem. The interesting thing about the mean value theorem is that you can use it to prove a whole lot of other things about calc. This probably wasn't done in your Calc 1 class. It may have been, depending on who taught it. But the mean value theorem is what you use to prove, for instance, that if the derivative is positive, then your function is increasing, and if the derivative is negative, then your function is decreasing, and so on. Your book redefines these notions here, increasing, decreasing. We skipped section 5.6, so this is not a recall, this is a define. And you can totally prove theorem 627 by using the mean value theorem. And I would kind of, again, read through these things more for results than for proofs. But I would try the proofs in this section. They're fun, and they're things that you can totally do at this stage of the game. You could scan over this further applications bit. And the inequalities bit also. This is fun, but nothing that we're going to concentrate too terribly much on. I would read over this section at the end about the intermediate value property of derivatives. You can kind of think of this as a restatement of the mean value theorem. Read the lemma, and then read Darboux theorem. It's a cool theorem, and I really like the example after it, 6213, where we can show that if we have a function that doesn't follow the result of Darboux theorem, it can't be the derivative of anything, which is a really cool thing that we can learn. So that's all for 6.1 and 6.2, and I'll catch you guys later.